we were looking at chiral superfields. Okay. So chiral superfields, we will look at all through. We wrote it as an expansion or expansion by y. I kept. Did I use x or y yesterday? I used x yesterday. Choose it. Normally I use y for chiral superfields. When I use this notation, or did I use that? It doesn't matter. Okay? X is equal to what are we doing? So I wrote something like a of x. Sin of x. Theta, theta. Is that what I wrote there? Now, there is a now this solution for phi of x. I told you that if I apply a particular class of differential, then I derived Yukawa terms, mass terms, and all that. But what about kinetic terms? Why is this so easy to use it? Okay, so kinetic terms come out actually naturally because if I recognize the idea, okay, the point is that when I wrote this thing, I didn't tell you one important issue. Okay, because I was in a hurry to introduce chiral superfields in a much easier way. That said, this is the solution, you remember it. Okay. Now, but this solution is in units or is in a variables where x is equal to actually x mu is equal to y mu, regular y mu plus I theta sigma mu theta bar. This is the units. So I combine the theta units and the y units together to call it as x. Okay. Now if I do that, now I can say, okay, this is a solution I got only because to give you a back picture of this, I need to go a little bit further actually. Okay. I will come to the back picture in a second actually. Just let me finish this answer. Okay. It turns out this solution for the chiral superfields is written when the variable is chosen to be this. When the variable is chosen to be this particular fashion. So now I put it back into this. I put it back into this. So what will be the expansion look like? Okay. So the expansion would be this is equal to a of y I theta sigma mu theta bar del a of x plus a of y. Sorry, because I am using the reverse. I thought I used loss a of y plus root 2 theta phi of x minus I by root 2 theta theta del mu phi of x sigma bar theta plus theta theta. So the first thing you see that you get your kinetic terms for the phonions, kinetic terms for scalars. Okay, they'll appear the moment because I'll tell you the backstory in a second, like I said. So, in addition to the kinetic terms, the chiral superfield, in addition to the kinetic terms, so you have to look at again theta theta products essentially. So you have to look at theta theta products. Okay. So when you do the theta theta products, say for example, for various things, it will appear in various forms in the superpotential.
So when we define chiral superfield, we said this is only a function of like one type, one thing like theta or theta or.
Right.
Now when we are extending this, like we are getting more theta and theta.
Theta theta bar. Okay. Now the point is that the chiral superfield, the reason why I said one theta form, this is written in this particular fashion, because for most of the interacting part of the Lagrangian is determined by this. The interacting part of the Lagrangian is completely given by one single chiral fermion. Because one single chiral fermion comes with one single theta. Okay, so one single form of the theta is the most important thing. Okay.
In general, it is not like phi is not just the function of theta. But
Phi can be anything.
Phi can be anything.
Anything. Phi can be the power series in theta and theta bar, because the superspace is essentially made up of del x mu theta theta. Superspace is made up of x mu theta and theta. Now the question was whether where you get the kinetic terms essentially. Okay, so you got the interaction terms in the previous class essentially. You also get the kinetic terms, but the linear, I didn't mention it, but from the superpotential, what are the terms you can get? This is the terms you can get if you expand it. But when you only take the theta theta components. Again, remember that you only take the theta theta components, and so there won't be any theta bar components coming from theta bar components coming from chiral superfield, from the superpotential. Okay. Okay. Even if we expand this one, they look like your kinetic terms. They look like your kinetic terms, but they are not polymorphic because they contain both theta and theta bar. Okay. So we need another function, which is the scalar potential. Okay, scalar function, which will give you the kinetic like terms. Okay, we'll come to that in a second. Okay, now this confusion should not arise essentially. When you expand x mu in terms of y, okay, will you get your kinetic terms? You will see that the terms which you will get essentially are coming from phi dagger phi type of terms. Okay, you need phi dagger phi terms and theta 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 bar for term. These kind of terms will give you the kinetic terms. It's obvious to you that these kind. So you need to look for combinations of phi which give you this kind of terms, which give you correct kinetic terms for your fermions and scales. Okay. This is now I'll tell you the backstory why this confusion arises. Essentially, the backstory for this. Okay. So none of these are holomorphic. Essentially, none of these are holomorphic. Okay. Now the backstory is, again, remember that we have a space which is x mu theta theta bar. Now you want to construct an algebra or a generator of supersymmetric transformations on this space. So this, I told you that there are these supersymmetric transformations, okay, and you can write these supersymmetric transformations exactly like a Lie algebras. Okay, but Lie algebras with fermionic generators, not just scalar generators. Okay, bosonic generators. These Lie algebras are essentially called graded Lie algebras. graded Lie algebras are for the supersymmetric transformation. Say for example x mu theta bar is equal to e power I, say depending upon your metric sign, let's just take x mu du plus theta q plus theta bar. Now see, what I did here is wrote P mu as your generators of translations, and then Q and Q bar as the generators of your supersymmetric transformations. Now, just like in any Lie algebra, what I do, the first thing I do is look for group multiplication law. Okay, I look for the group multiplication law. So I take two elements, say x mu theta bar times say x prime mu xi bar here I am multiplying from the left. Okay, in an exponential you have to use Baker-Hausdorff formula. Okay, using and then saying that this should be equal in another group element. Okay, just like what we do in Lie algebra and everything essentially. You will end up writing down your commutator algebra, your commutators. So what are the commutators you will end up with? Okay, what are the commutators you will end up with? Because operator would just go to x mu theta bar xi, let's just take xi bar. Let me just take to be 0 so that it becomes 0. So this goes to, you will see that this goes to, because I can just set x mu to 0 essentially. So this goes to x mu plus theta sigma mu theta bar theta plus xi theta bar. So this means that there is a shift. There is a shift from x mu to x mu plus theta less theta bar of the field values. Okay. So this means that these exponential operators can be equated to a differential operator. The group generators can be differential. Okay, in addition to this, commutator algebra, which is nothing but equivalent to P mu. Okay, the Q mu is essentially again equivalent to a differential operator. So you can give a differential representation for your Q. Okay, so your Q will have a differential representation. You write it in terms of this is your already seen notation. So this you get it just by substituting P mu is equal to mean is equal to minus I del mean. Okay, it's the same thing. But then you can actually using this identification, you can write Q alpha I wanted to avoid introducing short indices, but I wanted because I wanted to jump directly to supergroups. But anyway, I just wanted this one small doubt. If so, I don't want people to have it essentially because if they, I recommended very strongly this Western bagger. If they say what happened to kinetic term, they look like some kinetic terms. So, okay. So you have these differential operators. So key the supersymmetric generators are differential operators on superspace, on the Grassmann space. Supersymmetric generators are differential operators. Actually, they are not fully completely differential operators because there is also space derivatives. Q bar alpha dot is essentially minus plus I theta alpha sigma mu alpha alpha dot. Okay. So these are the two differential operators where I just said this is equivalent to G of x mu plus I theta sigma mu theta bar theta plus xi theta bar plus xi bar. Actually, there is one more term here minus I xi sigma mu xi bar. So this is the minus I xi sigma mu xi. Now the order of multiplication also makes a difference. So you got this particular differential operators by multiplying from left. But if you multiply with right, you will get a different kind of differential operators. You get a different kind of differential operators which satisfy almost very similar commutation relations. Okay? So these are called D's. So there are left differential operators and right differential operators. So the difference between the Q and Q D is that the plus sign. D alpha, Q alpha is L by del theta alpha minus sigma mu alpha alpha dot theta right bar alpha dot del V. I think I used right because it's an opposite direction multiplication. I'll get a plus sign. So okay. Because these are fermions, how you multiply, whether you multiply from the left or whether you multiply from the right, it makes a difference. And you may wonder why I am telling all of these things essentially. Okay, why I am introducing, which I promised I won't introduce. Okay, why I am introducing all these things, because I just wanted to introduce to you the condition, because this is the condition people are asking, you guys are asking, right, essentially, that uh, okay, so if q alpha dot 1 second, I'll just finish this, is equal to 2I sigma mu alpha alpha dot p mu, then sorry, then d d alpha d bar alpha dot is equal to minus 2I sigma mu alpha alpha dot mu. It's a minus sign difference only between these two things. So this is the real actual comparison. So there is a, just like, imagine, think them, these operators, don't think them as some this thing. Imagine there are left modes and right modes for fermions. Similarly, you have left-handed and right-handed operators for the Q's and uh, D's. Okay, the Q's are just like fermions, except their mass dimension is half. Okay, left-handed fermions are there and right-handed fermions are there. So what you are looking, so the condition of chirality, imposition of the chirality on a general superfield is to integrate out one particular chirality on the field, essentially. So you take the right, where is this one? The right operator, apply on the general superfield, and then you say this is the solution. This is the general superfield, say for example, and this should vanish. This should vanish. This is how you define your chiral superfield. This is the constraint equation you put on the general chiral superfield, and this constraint is solved very easily if I change the variables to y mu plus theta I theta plus theta, and that is the solution which you get if you this constraint. The general superfield, like I said, is a power series of mu theta theta bar will be some a of mu plus b b of x theta plus theta bar c of x theta theta c d x plus theta 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 or theta theta bar e of so on. So we should get, this is f, no, sorry, we used it as f, sorry. We should call it as f. So on, so, okay. So this is your, I can give the full form. So instead of calling it as I think let's use this notation. It's easier so that we will understand it because we will be consistent essentially. Plus theta phi of x plus theta bar chi bar of x plus theta f of x plus theta bar n of x plus theta sigma mu theta bm of x b mu of x plus theta bar lambda of x plus theta bar theta psi of x plus theta bar. This anyway is consistent. B of x. No, not this B. This is the power series essentially. So this is as expected. With theta we have a fermion. With theta bar we have a right chiral fermion. Generally, okay. With the theta we have left fermion. With theta bar we have right chiral fermion. Auxiliary field. Theta bar is also a scalar field. Theta bar. This is a vector field. This is a vector field because it goes with B mu. This is another fermionic field. This is another fermionic field, and this is okay. We'll use this notation. I think this is useful. So from this, I want to get the condition that d alpha phi x mu of phi is equal to 0. This condition I can solve it easily, okay, by putting y is equal or y mu is equal to x mu plus I theta sigma mu theta bar. In this condition, okay, this condition becomes easy. In this units, phi of y is equal to a of y plus theta equal to psi of y theta. So for chiral superfields, this is the notation with which we can do all the algebra very easily. So this is the backstory which I skipped completely essentially, okay, because it starts with graded algebras, okay, and then defining left operators as well as right operators, okay. Left operators are essentially your supersymmetric generators. The right operators are essentially you want to remove the right the chiral right chiral. So they are like left moving operators and right moving operators. The right operators you apply such that it vanishes, all the right operators will vanish, and that's how you define a chiral superfield from a general superfield on a notation.
So if you want to have,
Antichiral, you just use the opposite.
B alpha, and then also this variable y will be.
Then also the solution will be the it's symmetric essentially. It's symmetric in theta antichiral superfield.
But the general superfield, this variable x is the usual space-time.
Yeah, it's useful. Now I want to introduce scalar potential. Scalar potential. So what we have seen functions of phi, right? Essentially, we have seen functions of phi. We have seen this superpotential, and it gives you mass terms and Yukawa fields. So the dimension of the superpotential. We solve everything in terms of this particular thing, so it becomes easy. So then I want to introduce another important function, which is responsible. Like I told you, even if we expand, the reason is even if I expand, I don't know. You remember you got a point that even if I expand using y variables is sufficient. Okay, even if you expand in terms of these x variables, essentially, they look like terms which are kinetic, but they are not kinetic because they don't satisfy, those terms don't satisfy the holomorphicity of the chiral superfield, essentially. So the kinetic terms will not appear from, even if you convert from y variables to x variables, the kinetic terms will not appear from the superpotential. This is the most important thing that you should remember, that the kinetic terms will not come from the superpotential. So the functions which we have seen, the holomorphic functions, okay, are only giving you Yukawa terms or mass terms. Where are the kinetic terms coming from? Okay, where are the kinetic terms coming from? So this expansion I had written right earlier in right complex and they look like terms which are kinetic terms, but those terms are mixed in holomorphic, essentially. They are mixed in holomorphic. So let's now look at another function of chiral superfields, which is called scalar potential. Or scalar function is correct because it's not a potential term. Okay, most of it. Okay. In a scalar is one of the most important functions. Okay, the first function is what we saw was the holomorphic function or analytic function of W. Now this scalar potential is a real function for currents. Now this can have kinetic terms. Okay, this can have kinetic terms. Okay, because it's a real function. The earlier function was shown as an analytical function. So the only thing you can get is H Hermitian conjugates and everything you have to add. Okay, these are complex essentially. So this can have kinetic terms are real, always real, right? Kinetic terms are that's the reason. Okay. So what is the scalar potential? Scalar potential K of phi is a function of not just phi, but also phi diagonal. And the first term in scalar potential is nothing but phi diagonal. if you go into various other kinds of supersymmetries and supergravity and everything, it can have other terms. It can have a kind of, say, it can have some K, A, B, different kind of things. But we don't have that because this function is delta A. So this is, say, for all fields I, it's strictly the function which multiplies it is delta ij. Okay? If you want to write it as delta ij. Sum over all fields, phi I dagger phi. This should be always be multiplied. So, what is phi dagger? Let's compute this. Phi dagger is, let me expand this essentially. Again, let me write in terms of phi, in terms of these y fields for our simplicity. Y variables, a of y plus root 2 theta psi of y. The f of y, phi dagger of y dagger is equal to a star of y dagger plus root 2 theta bar psi bar of y dagger theta bar f star. So what is the supersymmetric invariant of the scalar potential? The supersymmetric invariant of the scalar potential is Sudhir invariant of the scalar potential is integral Sudhir is equal to integral d square theta bar k of phi bar or phi dagger. So this is the only thing which transforms as a total area. The only thing which transforms as a total area. So phi dagger, if I expand it in terms of theta, y is equal to x mu plus I theta sigma mu theta bar. If I do that expansion, essentially, phi dagger will be a star of x minus I theta sigma mu del mu is star of x plus 1 by 4 theta bar box of a star of x plus root 2 theta psi of x plus I by 2 root 2 theta bar theta sigma mu del mu psi bar of x plus theta bar theta bar. So this is the most general solution of the question which Nitija was asking. Is that this is the most general solution of V alpha of phi diagonal. So the chiral superfield is defined as D anti-chiral superfield. Phi diagonal is nothing but D chiral superfield. It's still a chiral superfield, but with its solution. Now what we need to evaluate is this one for every field. So this evaluation, you do it and I will write down the final solution. In the x components, theta, theta bar, theta bar, theta bar. In x components, now if you do this multiplication in y components, you won't get kinetic terms again. Okay? So the only thing which is available is epsilon f in y components essentially. That will remain. Okay? But in x components, if you do it, the final form of theta theta bar is f star f plus 1 by 4 a star box a star plus 1 by 4 box a star a minus 1 by 2 del mu a I star del mu j plus I by 2 del mu psi bar sigma mu psi j minus 1 by 2 I by 2 psi bar sigma mu bar del mu. So this is the theta bar component of phi diagonal phi theta bar. Okay, because there are psi I and psi j, let me put psi j. You can multiply any general term superfields, chiral superfields. You can put aj. But the kinetic terms are only when the limit is delta aj. The Lagrangian is delta aj. Now it's rotated. So you immediately see that phi diagonal phi terms give you kinetic terms of the correct type for the scalars and for the fermions. Nothing else. So the scalar potential gives you the kinetic terms for the. So can there be a situation that W is 0? but K cannot be 0.
W0 means massless and
Massless and no interactions. Okay? Massless free field theory should have scalar potential. If you have a theory, you will only with scalar potential. Okay? It's a massless free field theory. So though I introduced W later, K is the most important thing. So you can write a free field theory with scalar potential. So we are getting different pieces of the Lagrangian now. Now that we can build a completely free Yukawa theory in supersymmetric theories. Okay, so the total action with chiral superfields is L is equal to integral d power 4 theta k plus integral d2 theta. Okay. So with this, you rate a real function and analytic function with chiral superfields. You can deal with almost all interactions of not almost all interactions. At least we have now dealt with just with chiral superfields what you can do. All Yukawa interactions and everything can be done. Okay. So d power 4 theta, I am assuming here I am putting d power 4x. This is d2 theta, d2 theta bar. Okay. These are understood. Okay. So the main key is here compared to yesterday and today is that this change of variables is to be done when you are trying to derive the scalar potential. Okay, it won't make a difference in the holomorphic part of the potential of the field of the Lagrangian, which is given by the supersymmetric term. This kind of change of variables makes a difference for the kinetic terms essentially in the real part of the potential. So now let's look at gauge interactions. Now where will gauge interaction sit? Scalar potential or superpotential? Scalar, right. Why? Because they should be real. Okay. And where the kinetic terms are. Wherever there are the kinetic terms, you should modify them into normal derivatives will become covariant derivatives. That is your minimal coupling. So in a similar fashion, we want to do the same thing. So, but to introduce gauge interactions, we need to introduce a gauge fields, vector fields essentially. So the vector fields should be real superfields. Okay, they should be real fields. So start with a general vector So vector superfields, we start with a general superfield phi and demand phi dagger is equal to phi. Because we only want real components to survive essentially. Okay? We only want real components to survive. So this part of the superfield which satisfies this, we call it as B vector, standing for vector superfield. So B comes from the condition that a general superfield will become real. Okay? When it becomes real.
Scalar potential was also real, right?
Scalar potential is also real.
And here,
Uh,
because this
It is on the general superfield. The general superfield is the one which is at power series in theta, theta, theta bar. That I wrote it down, right? Essentially. So I think let me use this notation of this and value. Let me write it down here. This. So a general superfield phi is equal to some scalar term, some a of x, just to stick with the notation, plus theta, phi of x, it's a fermion. This is your general superfield. Now you can the so the general solution is general solution of a vector superfield V of x theta theta bar some real field psi of x. Okay. Then you always make real components by adding HC. Okay. So then you write theta chi of x minus I theta bar chi bar. Okay. And then similarly I by 2. For each component you can do it. So on so. I am just writing it to you so that it becomes easier to see. Where is the other one? Theta sigma mu theta bar Vn x. So what we want to do, okay, I'll come to this in 1 second. So I lambda bar of x plus I by 2 sigma bar del m chi of x. So there is this. Now theta bar, then the opposite minus theta bar I theta bar theta, but with a minus sign. Finally, lambda of x, instead of this, take the Hermitian complement, lambda of x, change the thetas, put a plus sign, sigma mu, del mu, chi bar of x. Finally, you put half theta bar d of x plus 1 by 2 box c of x. Now all of these things should be real. C, D, and C, all of them should be real so that your entire superfield is complete. Now the point is that what we want is this we want to, this superfield will not have any other role in physics other than in introducing gauge interactions. Okay. So we can choose a gauge where all the unnecessary components can go away. All the unnecessary components can go away because it's a gauge dependent quantity. Okay. So to understand why I wrote that solution yesterday, vector superfields are essentially that I only wrote these terms, right? This term, this term, this term, and this term. Only these 4 terms I said. These are the most important terms. Other terms are not important. To understand why these terms are the most important thing, I'll tell you how gauge interactions are introduced in supersymmetry. Okay? So gauge interactions are introduced on chiral superfields. Okay? Let's keep it as it is. Let's keep it as it is. So the way gauge interactions are introduced in supersymmetry are 5 prime, 5 goes to 5 prime, is equal to e power some arbitrary g, okay, some gauge transformation, tau a or whatever it is essentially generated, times instead of the theta which you notate, instead of the theta, wherever there is a theta, you introduce a chiral superfield, an arbitrary chiral superfield. Okay, you remember that phase which we write. So let's just say that on ordinary gauge transformation, you write it as some I power some I square some lambda a by 2 g a GA or something. Or let's take simple QD. Theta of x is the only thing which introduces sine something. That's it. Yeah. There is no complicated thing. Now instead of the theta, or if you are introducing abelian gauge fields, non-abelian gauge fields, I introduce I theta a tau a for each generator. Now instead of theta, I want to introduce a chiral superfield. I want to introduce a chiral superfield. So, because I want a supersymmetric invariant gauge transformations, so this theta is a normal field. No? This is like a scalar field. Instead of a scalar field, the lowest component is what is the lowest superfield in which the lowest component is a scalar field. Essentially, this is a chiral superfield. Essentially, which has mass dimension 1. Chiral superfield also has mass dimension 1. Okay, so I want to treat this theta. So instead of an arbitrary theta phase rotation, I phase rotate quote unquote by an arbitrary chiral superfield, and I phase rotate by an arbitrary chiral superfield. So this is how I introduce. So these are some generators. So I introduce gauge transformations. This is how I introduce. So let me not call it as phi because it's too many phi's actually. So what should I call it actually? So okay, let me change the notation such that I keep the tau as it is. So I'll write it as some G, PA, okay, and lambda. Let me call lambda as a rotating chiral superfields. This is good. Okay. There is some rotating chiral superfields. So chiral superfields. Generators. In a representation. In some representation. Now again remember what happens in QED. Okay, in QED I introduced equal right theta of x. Let's do U1 actually. We are going to do U1 only. Theta of x, some q, okay, some q. That's a charge. Correspondingly, on acting on psi, correspondingly, I introduce del mu and variation in del mu should go as del mu theta. Right? Remember that A mu minus A mu prime should go as del mu theta. So the variation in phi and the supersymmetric case, okay, the variation in the corresponding vector superfield will go as this is the difference in the two thetas. This is the difference between the two. It goes as a difference between phi, because why there is a difference here phi and phi dagger? Because the variation comes from the Keller potential. Okay, phi and phi dagger, because here psi and psi dagger exactly. So there is phi and phi dagger, phi dagger. Okay, we will do it in greater detail, but the variation essentially goes as this, or this is sinus per sinus per present. It goes as lambda plus lambda dagger. So we look for what is the SUSY invariant parts in lambda plus lambda dagger in fixing the gauge for V. Okay? Is it becoming too complicated? Okay, I'm just telling you. Okay, forget about all these things. Uh, Forget about all these things. We just say that because this is all for the motivation why I want to set all the first four terms. Okay? So if you look at 5 plus 5 diagram, if you remember 5 and 5 and look at it, it shows that the only these four terms are important. So this del mu theta is offset by the kinetic term in the Lagrangian of QE. When you are doing the minimal coupling essentially, this del mu theta is the offset by the kinetic term in the Lagrangian of QE. Exactly 5 diagram plus 5 term should be offset by the variation in this one. So I need to choose my variation, my vector superfield, such that the only thing which matters essentially is how it varies for lambda, any lambda plus lambda minus. Okay, so how do I know that? I will know that if I make a transformation, B goes to B plus 5 plus or lambda plus lambda dagger. I took the transformation. Okay, this is called a Taylor transformation, and there are several such transformations. When you do this transformation, you will see that C changes as this, D changes as this. Okay. So you can set a special gauge in which C, chi, M, N are all 0. And this gauge is called West-Zumner gauge. Okay, when you look into this thing, okay, when you write the expansion and everything, you can see that there are these things can be set all of them to be 0, and you can choose a particular gauge essentially. You can choose this gauge in which only this survive essentially. Only lambda, B, and D survive. You can choose this special gauges. So instead of working with a vector superfield with all these type of terms, what matters when you are introducing gauge interactions is that I forget everything else and just remember the formula in the West-Zumner gauge. There are some technical issues with West-Zumner gauge. We will not worry about it right now. Okay. It's called West-Zumner. It gives you very interesting features. So West-Zumner gauge is the most useful mathematical technique in which V is equal to the formula which you should all remember. Rest of the things we can forget. Why I said West-Zumner gauge, I told you. Okay. Theta bar lambda x. Just give me. Okay. Now there are. Okay. So. Okay. Let me just summarize in words so that you won't get lost. Essentially, that I introduce gauge interactions in this particular fashion. Okay, where I replace theta with a chiral superfield. Essentially.
Next time once again why we used chiral superfield?
Why I use a chiral superfield? Uh, because you cannot use any scalar function. Theta is a scalar function, local scalar field. Okay, but that won't lead to, it won't be invariance. It won't there won't be a gauge invariance in the superpotential unless I introduce a chiral. I will do an explicit thing essentially. Okay. It won't do it won't lead to an explicit. You won't have an explicit invariance of the, because you want everything to be supersymmetric invariant. The moment you choose a scalar just a theta, it's not supersymmetric invariant. Because any supersymmetric transformations on the top of this, then I have to go into component form and so on, so essentially. Because I want to write everything in a superfield notation. Okay, I want to write this way. I can see that how supersymmetric transformation works and the superfield notation. It's manifest and everything is clear essentially. So I do this, and then in analogy with QED, okay, where the variation in the vector superfield, vector field should be equivalent to derivative of the, or the difference, roughly the difference in the theta and theta bar, or essentially psi bar term and psi term essentially in the QED case essentially. Here it comes out to be lambda plus lambda diagram because it's the kinetic terms come from phi diagram phi terms essentially. Okay, phi transforms in one particular fashion, phi diagram transforms in another fashion. So the difference comes from this. This has to be cancelled by the variation in the superfield. So this gives me that I have to look for how the superfield varies when it shifts by lambda plus lambda bar. So this is the first transformation of a vector superfield. You will see I'm writing Keller transformation. Sorry. So very similar transformation also exists actually in terms of, okay, the Keller potential. Okay, I'll tell it later. Okay, so should be invariant under a transformation of this particular type, and demanding that I see that I can set some terms to 0, choose a special gauge, I demand certain terms to 0, and I end up having this particular form for the vector superfield. Okay, I remember all the other information, but for practical purposes, I only by heart this one. I forget about all the other equations. I only work with this equation and I only by heart this equation. Okay, that's the basic idea. So I remember the motivation point everything, but I only by heart this equation. Okay. So I remember my vector superfield only in the West Zumino gauge. Now in the West Zumino gauge, it has tremendous advantages. For example, V square is equal to, only one term is there in V square. V mu, it's easier to see, and V cube is equal to 0. So, if you put a vector superfield in the exponential, you know V cube is 0, V square is this particular term essentially. So, your exponential just truncates, and it's exactly truncates essentially. Okay, that is the reason why the vestibular gauge is so popular. Okay, that is the reason why the vestibular gauge is so popular. Okay, so it's a real superfield. Okay, so vector superfield contains a spin 1 particle and a spin half particle. And then it is a half 1 multiplied, and this is of dimension 2. D is of dimension 2, mass dimension. What is the mass dimension of vector superfield? Which we had 0. And this has spin 1 and mass dimension 1. Okay. So now we can start playing with. We have all the ingredients. Okay. I'll tell a simple rule. Okay, and then we'll apply it in the next class. We'll summarize the rules. Let's summarize the rules. And I should introduce one more function. What about kinetic terms per V? Or small vm? Where do they come from? So essentially in field theory, the kinetic terms are F mu F mu. Okay. So this introduces a new function. Okay. This introduces a new function. Okay, it's not really a function. It's called superfield strength. It's a superfield. Okay, which is also called a field strength superfield. I don't know how to write it. It's a curly W. It's a curly W. And in the vestibular gauge, it's very easy to write it down. So W alpha will not very too many things will write the final results. By definition is given by d bar d alpha d. And what matters is that this W acts like a superfield. Parallel superfield. acts like a chiral superfield. And when you do this, the components of W are essentially they're linear components. We don't have to worry about it. So because it acts like chiral superfield, we can write a corresponding superpotential term for this chiral superfields. And this is the first occasion in which a superfield gives you kinetic terms. Okay, a superfield gives you kinetic terms. That's the reason why we call it as a separate field strength superpotential, and then correspondingly we have field strength superfield. Superfield and field strength superpotential, which is represented by theta component again like a superfield, now you have the kinetic terms for V and also for the beauty of supersymmetry is once these formulas are known, you don't have to redo them again. They are etched in stone essentially. Okay. So now we have all the ingredients to build our first theory, a gauge theory. So what we do to build this first gauge theory? Suppose if I want to supersymmetrize QED, that's what I want to do. I'll start with supersymmetrizing QED or something. So the steps are as follows. All matter fields are mapped into chiral superfields. All gauge fields are mapped into vector superfields. And you get this, you immediately get the invariant Lagrange. Write down the invariant W K that's it. You have your Lagrange, which is supersymmetric invariant. Just follow these steps. Okay? And let's try to do it for QD. First we'll do normal QD because we might have forgotten. Okay? Just and then we will do this one QD. and then we'll do a map in between these two. Okay. And that's it. You have your supersymmetric field. Yeah, I know the last 3 classes are extremely tough actually because going through gory details and everything. But imagine if I do the same thing for full 1 semester. Okay, I'll lose everybody. Okay, but all you have to remember is these 3 equations. Okay, what is the equation for V? What is the equation for chiral superfield? And you'll be able to build your own theory. If you remember these 3 equations and the invariants, you can immediately start off writing your own theory. And then, of course, whenever you have doubt how did this come and we are worried about the origins of how these things come, then you have to go back and look at it. Okay. Otherwise, we can start off these 3 as your God-given equations and write your own supersymmetrized versions. And that's what we are going to do. Okay, we'll start with QD and then map it with supersymmetric QD and see how the theories are different in both cases. So our estimate is that QED should be, if you supersymmetrize it, it should give me QED plus scalar QED. That's what it should give you. Okay. Does supersymmetry impose some further constraints or not? We will see. Okay. Let's see next time. By the way, next week, how many of you are around actually? How many of you are going home and you're going? Okay.